All right, cool. All right, so ready for the shortest unit ever? Yeah. This unit is actually more like an introduction to optics, and it's light and color, and it's pretty fun because a lot of the stuff you've actually seen before, maybe not, but I enjoy it. So let's see if I can get my top spinning. There it goes. Okay, so light's a transverse wave. Okay, we talked about this briefly, and it's electromagnetic radiation. Light's an electromagnetic wave. Now, what we usually consider light is stuff that we can see. Now, first and foremost, let's talk about cartoons. Okay. When I was growing up, if the superhero was seeing something, or the kid was seeing something, they draw these little looking beams, like he's looking out of something. When you see something, is light going into your eye, or is light going from your eye?
Into your eye.
Wrong, both.
Hi,
Yeah. Visible light is going into your eye. That's how you see things. But everything that is at normal Earth-like temperatures emits infrared light. Everything emits infrared light. So if you could see in the infrared, you could see in total visible darkness. Easy enough. Okay. And some insects and birds can. They can see in total visible darkness because everything emits infrared light. It comes from the vibration of molecules at normal Earth-like temperatures. We're not going to go into the math of that. Just realize that if at normal temperatures, everything emits infrared light.
What happens if it's exactly no movement? Like what you see?
If it was at absolute zero, then it would become invisible. But as long as there's molecular movement at normal Earth-like temperatures, you're going to get some infrared light. Now, it's kind of like a toaster. When you heat up the little filaments in the toaster, you can see the toaster emit visible light because they've shifted their energy, if you will, higher. So this is infrared right here. When you heat up your toaster, those elements start increasing their thing until you can actually see them. If you could see in the infrared, your toaster would look like it's glowing even when it's turned off. Kind of cool. Light bulbs do the same thing. Incandescent light bulbs, the old style light bulbs that have a little metal filament that burns out, what that would do is it would run voltage through it, it would heat up, and then it would heat up to the point where it could produce visible light. Now, I talked about stars and why we call stars black bodies. Stars produce all the electromagnetic radiation. They produce the whole gamut. They produce long radio waves. They produce visible light, thank goodness. They produce infrared light, oh, it's nice and warm. And they produce ultraviolet light, ah, it's gonna kill you. And they produce hard gamma rays and X-rays, also that'll kill you. The good news is these are ionizing radiation, and you're protected by a shield around the Earth called the magnetosphere. No joke, it's called the magnetosphere. So we'll talk about magnets later, but you're protected from most of the really nasty stuff. Okay, so we also talked about how all light, all electromagnetic radiation travels at the speed of light, 3 times 10 to the 8 meters per second. That is in a vacuum. And it's like 2.997 blah, blah, blah. And it's it's slightly slower in air. So we just kind of say, let's just make it 3 in air or in space. Now, that's not the speed of light in glass. When material has to go through, when light has to go through glass or other transparent or translucent materials, it slows down. It's kind of like this. Electromagnetic radiation is the transfer of energy. And when an electromagnetic wave hits material, the material gobbles it up. The electrons in that material jump to a higher level. Remember your quantum in chemistry? We were talking about the levels jumping up and jumping down? Okay, so the light comes in, the material causes the electron, or the electron and the material jump up, they jump back down, and they send the electron on. Okay. So, Sophie, here's a ball. Remember, no crumbs. Make sure you pick up your makeup. Yeah. 5th period's complaining about your messes. Okay, so make sure you clean it up. So, this is what I'd like you to do. I'd like you to pass the ball to Sarah. Sarah's going to pass it to Emily. Everybody counts. 1001, 1002, 1003, 1004, 1005. Hey! Okay, so Christian got up in about 1005 seconds. About 5 seconds. Now, Sophie, you ready to catch? Now, throw the ball back to Sophie. 1001, oh, that was fast. So light travels a lot faster when there's nothing getting in the way. But when light gets in the, or when materials get in the way, the materials absorb the energy, electrons jump up, electrons jump down, they pass it to the next molecule, electrons jump up, electrons pass it to the next molecule. So the more dense the molecule is, the blank, the speed of light in it. Slower, yeah. The more dense a material is, the slower the speed of light is. Diamond, in fact, is so dense, its speed of light in the diamond is not even 2 times 10 to the 8th meters per second. It's barely over 1. It travels about a third the speed of normal vacuum light or air light in a diamond, which is why diamond has all the crazy properties it does. We're going to get to that more later when we talk about optics. Just realize that as materials get more dense, the speed of light in them slows down. Okay, any questions? The math we're going to be using is nanometers. Nano is 10 to the negative 9. So between 700 nanometers and 400 nanometers, we have our visible light. Between, okay, did you realize that 700 times 10 to the negative 9 is the same as 7 times 10 to the negative 7? Okay. And 400 times 10 to the negative 9 is the same as 4 times 10 to the negative 7? Okay. So between 700 nanometers and 400 nanometers is visible light. Anything slightly higher than that is ultraviolet. We can't see in the ultraviolet. Maybe in a couple thousand evolutions of human existence, maybe we can, but we can't right now. We can't see in the infrared either. Some insects and birds can. So there are insects and birds that can see in total darkness because they can still see infrared, which is kind of cool. That's fun. X-rays. Here's X-rays. X-rays can see smaller things, hard X-rays, gamma rays. Yeah, we'll talk more about that later. And then infrared, microwaves. Radar is right here. Radar is technically not radio waves, it's microwaves. Also, the waves coming out of your pocket right now are very tiny radio waves. They're kind of large microwaves. Don't worry, they can't hurt you. But that's what your phone's producing right now.
They don't produce any harmful waves.
No. The material is simply too large to interact with the atoms in your body or your clothes. Unless it's a metal. The long waves will actually hit metal and get absorbed by metal. But that's it. So no one's upset that this thing is still going?
Oh my god.
I'm a little.
We're all still asleep, apparently. It's still going. It's just not lit up anymore. It's still going.
Why? I want it lit up.
Because you're all still asleep. Oh, why won't it light up? I don't know why it won't light up. It only stays lit up for the first couple minutes. Yeah.
Wait, how long will it
I
go
don't
on
like
for?
that.
Until the battery runs out. It's got a really slick inductive battery that keeps it spinning.
Oh.
I was
Yeah.
like, what?
Yeah,
Like
I have
that was a
a
powerful
pendulum that has a magnet in the bottom too. That's battery powered, so it just keeps going forever. But yeah, the top has actually got a little calculator battery in it, and it'll just spin forever until the battery runs out. I think the battery's almost running out because it's trying to turn itself. It's trying to light itself up, but it can't light itself up. But anyway, that's fine. Okay, so we're still using the same formula we used before. That velocity is lambda times f. So speed is still wavelength times frequency. But fun for light waves is we're going to start using the letter c to represent 3 times 10 to the 8th meters per second. So when we are talking about light speed, speed of light in air or a vacuum, we're just going to call v c. Just like g is a special a, c is a special v. Okay? Just like g, the acceleration of gravity, is a special acceleration that we use on Earth, c is a special velocity that we use when we're talking about light waves traveling through space or air. Do you understand that when I say light waves, I mean the whole electromagnetic spectrum? Okay. So radio waves are light waves, but you can't see them. That's right, they don't interact with the sensors in your eyes. Microwaves are light waves. Yeah.
Where infrared, that's above the spectrum of visible light.
Below. Lower in energy, but longer in wavelength. Okay, we're going to talk about that too. So radio waves have very, very long wavelengths, very low energy. Infrared have longer wavelengths than visible light and less energy per photon. Photon is a single boom of light, a single wave, called a photon. Technically a particle of light. Yeah.
Okay, so there's like little like gaps in between like the different sections. Does that mean it can be classified?
I did that so you could see it.
Ah.
Yeah, I did that so you could kind of just see it. So yeah,
Is that
and again, is there overlap? Yes, there's overlap. So if you go like, well, what is 10 to the negative 1? Is it a radio wave or a microwave? You could be like, you can call it whatever you want.
Okay, so there are like overlapping.
Yeah. And again, visible light, we say 400 to 700 nanometers. Some people just can't see into like 700. Some people can see like 710, like see like very deep violets. Some people can't. So in general, we say humans can detect 400 to 700. It's kind of like sound waves. Some people can't hear 1800 hertz or 18,000 hertz. Some people can't. We just kind of. Yeah.
Never mind. I have a question, but
Understood. Landon.
So X-rays, gamma rays, that's all to the right side of visible light, and those have. So you say infrared has less energy per photon or proton.
Photon. Photon.
Okay, so those have more.
Yes, yeah. So anything on this side has a higher frequency, a
So
shorter wavelength,
Okay.
and a higher energy. Energy is going to be related to frequency. I'll go ahead and write the formula. We'll get to that eventually, but let's go ahead and write the formula. Energy of a photon is going to vary with frequency. So the higher the frequency, the more energy per photon. And it's photon is spelled pho. Let's have a bowl of pho. Photon.
That's fun.
A ton of pho. Let's have a ton of pho.
So E varies inversely with it.
No, E varies linearly. E varies proportionally with frequency.
Okay.
Yeah.
And E was not frequency, energy.
E is frequency.
Oh.
Sorry, E is energy. Yeah, E is
Yeah.
energy.
I
Yeah,
was
that's
like,
frequency.
is it
Sorry.
frequency?
And if you wanted to put lambda in there, you could basically say that E varies with the inverse of lambda if you wanted to, because frequency and wavelength are going to vary inversely if you wanted to go that direction. Okay, make sense so far? Okay, any questions? Moving right along. Okay, so we have three words that we like to use when we're talking about light interacting with materials. They are, you can't go through it. You can go through it, but it gets moved around a lot, or it goes through it pretty much in a straight line. Okay? If it goes through it pretty much in a straight line, we call it transparent. Our corneas are transparent. Okay? Glass is transparent. If light goes through it, and it basically transparent means to show through or to move through. Transparent. So that means that light appears to go through it unchanged. Appears to be unchanged. We know that when light goes through any material, what does it do? It slows down. But the reason it appears to be unchanged is it slows down going through the material and then speeds up again as it leaves the material. That's important. As light goes through my glasses, it slows down as it enters the glass, or polycarbonate, or the material. It slows down as it enters the glass part of the material, but then it speeds up again as it leaves the material. Then it slows down again as it enters my eye, and then it gets absorbed and turns into, makes a chemical reaction in my eye. But, so it doesn't stay slow. That's the important thing. It slows down in the material, speeds up again when there's nothing in the way. Cool? That's transparent. Translucent literally means past light, whatever. So translucent is the light passes, but it gets bounced around a lot, making material look fuzzy. This is what happens when you take a hamburger patty and you rub it on a piece of paper. You're like, I can see right through it. Never done that before? So go home, get some mineral oil or vegetable oil, and pour it on some paper. You can like see right through it. Look, Mom, I can see through the paper. And one of my favorite, you can use this in your just general vocabulary, is opaque. Opaque. O-P-A-Q-U-E. It literally means blocking. It's like, stop being so opaque. Stop being so confusing. Come on, Mr. Strachan, stop being so opaque. Be more transparent. I wish my parents would be more transparent about their intention to give me a car. They just keep being opaque. And then whether light gets absorbed or what light gets absorbed or transmitted depends on whether it's a pigment or a dye. Not terribly important, but I'm going to mention it anyway. So that's opaque. Your desk is opaque. Your skin is translucent. You just got a lot of it. Okay. Any questions so far? Moving right along.
Wait.
Oh, okay. What? Sorry.
What do veins?
Oh, I did put that there. I was like, I need to talk about that. Okay, so what do your veins and the sky have in common?
They're both translucent.
They're blue.
They're both blue, right? They're both blue. So if you, I realize the light's not very good, but if you look at your veins, you're like, hey, I got blue veins. If you have really dark skin, you might have green veins. So like, hey, look, my veins are blue. The sky is blue. It's blue back over. So it's blue over there. I guess the sky is clear over that way. So is air blue?
No.
No.
Is your blood blue?
No.
Is your blood ever blue? Yay! No, it's not ever blue. No, it's not. Weren't you here last year? You were in chemistry last year, right? We talked about this?
Yes.
Okay, so, yeah. Oh, it stopped. So, your blood's never blue. Your blood is only red. Your blood can basically be three colors. Dark red, red, and brown. So, it's dark red when it doesn't have a lot of oxygen in it. It's bright red when it has oxygen in it because the blood becomes less dense and oxygen, and it's also bright red when it has carbon monoxide in it. And then it's brown when it becomes a scab.
So when say you like get impaled by your car and your blood spills out, what color would it be?
Red.
Is it like so in all movies it's like super dark, but is it really not that dark?
Oh, it's funny you should mention movies, because it gets darker over time. As the blood oxidizes, it does get darker over time, and as liquid evaporates, as water evaporates out of your blood, it does get darker over time. Fun fact, anyone ever seen a video on YouTube, it's like what had to have happened, or the discussion that had to have happened? It's like, so they pretend a discussion that happened before they made a movie. I had this image in my mind that somewhere in the 50s, when they started using colorized film, they had a discussion about what color should we make blood. And they went to a doctor and said, what color is a dead body after the blood has dried? And he said, brown, because it is. And then they're like, hey, let's use brown. And then someone would be like, how come the body is covered in poop? So they still use red. They tend to use Caro syrup and red dye to represent blood. But realize that a crime scene is mostly not red, it's mostly brown. Because you know how fast your blood becomes a scab? Yeah, pretty fast. That's how fast the crime scene would turn brown. But people don't want to see brown in a crime scene, they want to see red. You know, like CSI, there's like red blood everywhere, like they swab the red blood. It wouldn't be red, it would be brown like a scab. But anyway, so they had to like, let's just make it red and knock gross out of the way. But anyway, so there you go. So your blood's never blue, yeah.
Well, I thought like it was blue inside you, and that's why you didn't have like oxygen. Then it came out, and then when you hit oxygen, it was red. So it is blue on the inside.
Yeah, unfortunately, there's even nurses that think that.
Great.
Yeah. No joke. I have encountered nurses who thought your blood was blue and then it becomes red when it goes out of your body. Your blood is never, ever, 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 ever blue. And the reason some nurses think that is in biology textbooks, they show venous blood, blood in your veins, to be blue as it's on the way out, and as on the way from your body to your heart, if you will. So venous blood is on the way to your heart and your lungs. And arterial blood is from your hearts and your lungs. So basically, body to internal organs is blue, and internal organs to the rest of your body is red. So they can differentiate between a vein and an artery. So a lot of people just assumed that your blood is blue. It's never blue. In fact, if your blood ever does encounter the air, they have to throw it out. So your blood's never blue, ever. So why do your veins look blue?
Is that the light, only the visible light that like can pass through?
Okay, your veins look blue for the same reason the sky looks blue. White light is composed of all colors of light, but not all colors of light interact with all molecules the same. Red light, for some reason, tends to get absorbed very, very, very well by water. What does your skin have a lot of? Water. What does the sky have a lot of? Water. So the red light gets absorbed and the blue light gets scattered or sent through. So when you look at your veins, what you're seeing is a tiny layer of skin over your veins, and the red light is getting absorbed in the water molecules of your skin. And the blue light is going bounce and making it to your eye. It's like all the light's going boing, but the red light's staying there and the blue's coming back, so it looks like your vein is blue.
So there isn't really such thing as color. It's just light. It's like
Yeah,
the
it's just-
color reflecting. off
Exactly.
the
It's color is what your brain calls the frequencies of light that cause a chemical reaction in your eyeball.
So if
Yeah. And it's also really fun. You're like, dogs are not colorblind. They have the receptors for blues and yellows. So they're not colorblind like we think. They're like, oh, dogs see in grayscale. No, they don't. They just, there's a lot of colors they just can't see. They can't see reds and greens, but they can see blues and yellows.
So why, like, if your eyes are bloodshot, why is that like red, not green or blue?
Oh, that's just there's too much blood there. You're just swollen. Your eyes are just the little arteries in your and veins in your eye have become swollen. And in case you're wondering why the veins are blue and not the arteries, the veins are closer to the surface because they're higher pressure. They basically your blood's like veins come to the surface. Yeah.
colorblind people just don't like have the chemical reaction to see that.
Precisely.
So they do see things in grade school if you're like completely colorblind.
That's a little dicey. Some people, it depends on what kind of color blindness you have. Some people utterly lack the chemical reactions and the chemical receptors for certain colors, and they can't tell different colors apart because there isn't anything to say this is this and not this. Does that make sense?
They're not different. They have like not different shades of dark.
Exactly, not different shades. Just now realize what the part of your eye that determines brightness is different than the part of your eye that determines color. So a bright yellow, they could differentiate from a dull red, even though they couldn't see red or yellow. Does that make sense?
Yeah.
Because they can detect the brightness. Okay. Question?
So how does temperature affect that? Like what we can see through our skin and stuff like that? Because like when it's hotter, notice your veins are bigger or whatever.
There's just a higher pressure. They're just pushed closer to they're just pushed closer to the edge of the water balloon that is your skin. The thin layer of you that keeps all your goo inside. Okay, so we talked about the inverse square law with sound. So the inverse square law, once again, occurs anytime you measure something that is a three-dimensional phenomena over one dimension. And light propagates in 3 dimensions, but if you look at it how it changes over 1 dimension, you use the inverse square law. So I hope this diagram helps more than this. If you had a flashlight and you held a screen, a 2-dimensional screen up, it would make a box. It would make one box, and that box would have a brightness value at 1 meter. At 2 meters away, it would make 4 boxes, and each of those boxes would have 1/4 the brightness of the first box. If you went 3 meters away, now they're tripling the distance, then you would get 9 boxes, and each of those boxes would have 1/9 the brightness of the first box. So the energy is not lost, it's just spread out. Does that make sense? So if you're like, okay, it's got this intensity, it's got 1 intensity, it's at the same distance or the same area, it gets 1/4 the intensity, twice as far away. And the same area, it gets 1/9 the intensity, 3 times far away. Now, the reason we use the inverse square law like this is our eyeballs tend to see things in 1 dimension. Okay, so I'm like, oh, that has a brightness of 10. That has a brightness of 2.5. That has a brightness of 1.1. 1/9 of 10. Make sense? That's the inverse square law. Oh, lasers. Boop. Lasers do not, they don't diffuse, so they don't get less bright over distance.